Alright folks, welcome back. So today I want to continue by looking at another paper on automatic patch generation or techniques for fixing bugs automatically. And the paper I'm looking at today describes a system called Getafix, which was developed by folks at Facebook Research, and this was published in the very recently concluded OOPSLA 2019 conference. Now, in this channel, I've looked at a few other papers in the past in this line of research. I'll link those in the description, but this paper takes a slightly different starting point from the ones we've looked at so far. Instead of looking at real bugs in the code, it starts with the output of static analyzers. Today, it's very common to have static analyzers fully integrated with the code review process, so that when you submit a patch into the code review tool, it will already run a battery of static analysis tests and point out various issues that it found. And these are things like, potential null references or incorrect idioms or incorrect uses of well-known APIs and so on. And you see these warnings in your code, and then as a programmer, you can make the judgment on whether you want to go ahead and fix them. The problem that this paper is trying to solve is to reduce the effort it takes to fix those static analysis warnings by building a system that simply suggests the fixes themselves. And then as a programmer, you simply look at the suggested fix and accept it if it looks okay to you. Now, the targeting a specific class of bugs. You have really simple bugs with very simple fixes like marking a method private or marking a field as final. And those don't really take a lot of effort to even fix right away. On the other hand, you have large complex bugs like a major piece of functionality missing or being incorrect. This paper tries to target bugs somewhere in the middle where the fixes are what they call repetitive but still non-trivial. A good example of that is null pointer exceptions. If a programmer sees one, they will relatively easily know how to fix it, but the exact nature of the fix depends a lot on the surrounding code. The goal of Getafix is to suggest human-like fixes. In other words, they want to suggest fixes that humans would have idiomatically written. They shouldn't look machine-generated. And also to do it fast enough, so on the order of seconds, such that they can be incorporated into a real-time code review process. Now, like I've said on this channel, we've looked at a few papers along these lines before, and the authors here try to contrast their work with some of the other research in the automatic patch generation field. Now, one very common technique in the existing research is the generate and validate approach. At a very high level, you build a model and use the model to then generate a number of fixes and then rank and validate those fixes using some strategy. Getafix makes a few different design choices when compared to prior work. The first one is that when it generates patches, it does so without any validation. It generates patches and then it ranks them, and it only validates the top ranked fixes, not all the ones that it generates. The other big difference is that a lot of the existing research uses a comprehensive test suite as a validation filter. So when they generate a patch, they will then run a test suite to verify that the generated patch passes an offending test. They also use a test suite to isolate where the fault occurs. And again, Getafix is different because rather than a test suite, it uses a static analyzer. It uses a static analyzer to pinpoint the location of a bug, and it also uses a static analyzer to then validate a generated patch, because the generated patch must not generate the same warning that the static analyzer found previously. Here's an overview of how the entire system works. Again, we'll separate this into a learning and training phase and then a prediction phase. The input for the learning phase is a collection of static analysis bugs or static analysis warnings and their fixes. So they get this from their revision history on their code base. This data is fed into their learning algorithm, which works at the level of abstract syntax trees, and we'll see in more detail how that works exactly. They build a hierarchical model of abstract syntax tree patterns, which is then used to suggest fixes for a new static analysis warning. And finally, it's very important to be able to rank these fixes in confidence order. So they have a ranking algorithm which ranks these fixes before presenting it to the programmer. The first step in analyzing the learning data is to construct abstract syntax trees of the code before and after a fix. And they do this with some surrounding context in the code as well. Now note that when you diff the abstract syntax trees for a specific patch, the diff is going to be very specific to this particular patch. The next step is to be able to generalize from that and extract more generic patterns that can be applied in other situations as well. And the way they do this is by essentially introducing variables or placeholders, what they call holes in the paper, into the abstract syntax trees. And these are places in the abstract syntax tree where you've abstracted away a particular specific part of the tree where you could substitute in other things. So for example, if you look at the statement A equals A plus A, the very specific abstract tree pattern for that looks something like this. And if you look at the specific statement B equals B plus 2, the abstract syntax tree for that looks like this. If we were to try and extract a general pattern from both these abstract syntax trees, it would look something like this, where we utilize a hole H0. So the left-hand side is H0 and the right-hand side is H0 plus H1. So that generic pattern would be able to represent both of these more specific abstract syntax trees. They call this process anti-unification, and what this basically does is give you the least generalization of a pair of abstract syntax trees. And once you have this anti-unification algorithm, you can use it to construct a hierarchical tree of edit patterns. You start with all the concrete edits and then take pairs out of those and combine those pairs to make a generic pattern, and then combine those resulting pairs and so on. And this will eventually give you a tree where the leaf nodes represent all the specific concrete abstract syntax trees, and the higher you go up in the tree, the more generic your abstract syntax tree patterns will become. Let's look at an example of how this tree formation would work. If you look at these two sets of diffs, you'll notice that the only difference here is the method that is being called on an object called content. So in one case it's content.remove, and in another case it's content.render. So if you were to generalize this, you would introduce a hole or a variable which represents the method being called. You could then take this general pattern and try to merge it with another diff and get a new resulting even more abstract tree pattern. So that was how we build our model. We take a lot of training data in the form of patches with their static analysis warnings, and then we make abstract syntax trees out of them. We diff those abstract syntax trees, and we try to make generic patterns out of those abstract syntax tree patterns. This gives us a tree of abstract syntax tree edit patterns. And that's what we're going to use to then generate and rank fixes. The basic idea is pretty simple. We want to find matches between the tree patterns that we have learned during the learning phase with the abstract syntax trees of buggy source code. And to do that, we first find a subtree in our model that matches the context before our buggy source code. And then we try to instantiate all the holes or all the variables in the abstract syntax tree pattern with the specific code that we're now seeing and trying to fix. And then we substitute in the context after the code that we're trying to fix. That's all very well and good, but when presenting these suggested fixes to a programmer, it's very important to rank them in some order of confidence. And Getafix does this based on 3 scores. The first one is what they call a prevalence score, and the idea behind it is that if a way of fixing a bug is very common, then it should get ranked higher. The second score is what they call a location score, and this measures what fraction of bugs were fixed by a pattern by applying that pattern exactly Z lines away from the warning location. And the last one is a specialization score, which assumes that patterns that are very specific or that are applicable to a very specific code location are more likely to fix a bug because they fit their surrounding context very well. And the final ranking score is a product of these 3 scores. Let's look at the results they achieved. We want to see how often the number 1 suggestion is the correct one, the one that human programmers will accept as a fix. We also want to see then how often the correct fix is among the top 5. And what they find here is that their top 1 accuracy ranges between 12% and 91%. And if you open that up to top 5, it ranges between 19% and 92%. You'll see that it does really well on some categories of bugs like boxing or unboxing primitive constructors, and it does very poorly on other categories of bugs like null pointer exceptions. The explanation for that is boxed primitive constructors can be fixed with a very small set of patterns that you see repeatedly, and so the model picks that up and suggests it easily. On the other hand, null pointer exceptions have fixes that vary a lot, and the model has much more trouble capturing that variation. But of course, the most important measure of success is how human programmers work with the system. Do they accept the suggested fixes? And what they found was that in about 42% of the cases they do. In 10% of the cases, the fix was a pattern that Getafix would have suggested, but it just did not rank highly enough. But from this, the authors conclude that the overall idea of suggesting fixes being integrated into the code review process is a positive thing, is something that developers use, and their model can do it with a latency that's low enough for it to be used within the code review process. So that was a quick look at another paper that tries to use machine learning for fixing bugs or for generating code. I hope you enjoyed that, and I will see you next time. Thank you very much.